Our next theorem will look very similar to a theorem we had involving sequences. Theorem 2.5 starts off with two functions f and g, both with the same domain, capital D, and going into R. Let those functions be given, and let x naught be an accumulation point of the domain D. And let L be the limit, the real number, limit, as x goes to x naught of f of x, and m is the real number, the limit as x goes to x naught of g of x. So the theorem states that if f of x is less than or equal to g of x for all x in the domain, then I imagine you know what to put here. Then f of x is smaller than or equal to g of x for every x in the domain. That would mean that the limit of this function as it approaches x naught is going to be less than or equal to the limit of this function as it approaches x naught. So we would have, which one's which? L less than or equal to m. So that's the statement of the proof. The statement of the theorem. The proof I'm leaving for you to do for homework, but I'll give you maybe just a little hint. Use either the definition, which means the delta epsilon approach. Use either the delta epsilon approach as in theorem 1.12 that we did for sequences. If you don't remember that, we did it by contradiction. We supposed to the contrary, for the sake of reaching a contradiction, we said, oh, suppose that m is less than L, and we reached a contradiction. So that's one approach, or use sequences and apply theorems 1.12 and 2.1. That's just hints for how you'll do this homework problem.